Welcome. Today, I'm going to be introducing the six main trigonometric functions that we'll be using for the rest of this unit. But before we do that, I want to briefly remind you of where we left off. So first of all, we went over on the formation of the unit circle. And as a reminder, the unit circle is called the unit circle because it has a radius of 1. So from the center to any point along the circle has a value of 1. And the reason this is important is because it allows us to represent every possible right triangle or a similar version of every right triangle. So if we take any point along this unit circle, this can be represented by the x and y coordinates of this point. And by using those x and y coordinates, each point will represent a right triangle. And because it is a full circle, it represents every possible right triangle depending upon what angle we put it. So the coordinates of each of these points on the unit circle, x comma y, represent the legs of a right triangle. And again, depending upon what angle theta we give, okay, this will represent different right triangles, and we can form any possible right triangle, or at least a similar version of it. Okay, and it's based on this similarity and properties of similar triangles that gives us the unique and amazing properties that make right triangle trigonometry work. So similar triangles all have certain properties if you remember from geometry. And the main property that we're going to be exploiting here is that for similar triangles, um, they can be scaled to different sizes. And based on the fact that all the angles are going to be the same, the scaling has to be proportional. So essentially, all similar triangles are the same shape, and they're just dilations or magnifications, either smaller versions or larger versions. And this unit circle is a particular dilation where the hypotenuse is 1, and the x and y coordinates are some values between -1 and 1 for both x and y. Now, what this allows us to do is because they have the same shape, we can do manipulations and exploitation the fact that they're proportional. And what this means is that if you take two proportional sides of any right triangle, so for example, let's say we have a 3, 4, 5 right triangle, we have another similar triangle would be the 10, 8, 6, and any multiple of that. And because all of the sides have to be proportional, if you take any two sides, so for example, the 6/8 here, so this side and this side, and we take the same sides on a similar triangle and we form a ratio of these end up being the exact same value, just magnified. And it's because of this that this circle can represent every single possible right triangle, but instead of being, you know, a hypotenuse of size 20 or 15 or zero point 0.2, it's specifically the similar triangle version where the hypotenuse is 1. Now, it's because of this property that all the sides are proportional that we form our six trigonometric functions. And most of you have heard of these before, and most of you've heard some of the relationships between some of them, things like SOHCAHTOA, so forth and so on. We're going to go specifically into how these are every possible combination of our x, y, and hypotenuse of 1. So specifically, the first major trigonometric function that we will discuss is the sine function. Um, Along with the sine, we have cosine, and tangent. These most of you are familiar with. Some of the lesser known ones that you might be less familiar with, are cosecant, secant, and cotangent. Now, again, these six trig functions are formed from the fact that we have three sides of a triangle. We have x, y, and hypotenuse. So if we write it as x, y, and hypotenuse, not specifically the version from the unit circle, all the combinations of one divided by the other would be x over hypotenuse, x over y over x, y over hypotenuse, and hypotenuse over x, and hypotenuse over y. So these are the six possible combinations we have of one side divided by the other. Now, if we take these combinations, each of these will line up with a specific trig function. Now, most of you don't see the trig functions spelled out like this. Most of you are more familiar with how they look on a calculator. So sine is usually sin, and it has an input. Now, the input of sine is an angle, and it can be an angle in either degrees or radians. Now, when you're inputting it in degrees or radians on a calculator, the calculator will not know which one you want to use. So if you're using a TI-84, you need to press the mode button and check to make sure it's in the unit you want to input. So if you want to use degrees, make sure it says degrees. Radians, make sure it says radians. Okay, so the sine of the angle uses the relationship between the opposite side and the hypotenuse. So this would be y over h. Now, cosine, which looks like cos or cos, also takes in an angle and now uses instead of the opposite side or the y coordinate, it's going to use the x coordinate over the hypotenuse. And the tangent, written as tan on the calculator, will take in an angle and output a ratio of the opposite side, or the y, over the x. Now, these are the ones you're more familiar with. It's the ones you've used in geometry and in algebra 2. Um, there are three others, as we mentioned before: cosecant, secant, and cotangent. The reciprocal of sine, aka hypotenuse over the y coordinate, is actually going to be cosecant of theta. Now, this is written in your calculator as CSC of theta. The reciprocal of cosine is going to be hypotenuse over your x coordinate, and that's going to be written as secant. And then finally, cotangent will be written as COT, and this is going to be x over y. So these are just the reciprocals of the three base functions that we've learned before. Now, if we're applying these to the unit circle specifically, the value for h is going to be set to 1, because all of these are similar triangles that specifically have a radius of 1. And so that means our sine, instead of being y over h, our sine of theta is just simply going to be the y coordinate of that point. The cosine of theta is simply going to be the x coordinate, and the tangent of theta is going to be the ratio of sine over cosine, or y over x still. Now again, the inverse, or sorry, the reciprocal trig functions, um, cosecant, secant, and cotangent are simply the reciprocals of each of these. So cosecant of theta equals 1 over y, secant of theta is going to be 1 over x, and cotangent of theta is going to be x over y. Now, to put these in on the calculator, for the TI-84, there are no cosecant, secant, and cotangent buttons. You literally take 1 and divide by sine of theta. For cosecant, you take 1 divided by cosine of theta for the secant, and 1 divided by tan theta for cotangent. On the TI Inspires, these are a little bit um, nicer for putting in these reciprocal trig functions. You press the trig button on the left-hand side, and it'll give you a menu of all 6, sine, cosine, tangent, cosecant, secant, and cotangent. Because each of these trig functions input specifically a angle, the way it works is that this angle, so if we do like an input output, so this angle, what it does is it, or this function translates this angle and outputs a ratio. So for this, our angle can be in either degrees or radians. And by specifying the degrees or radians, it actually gives us a specific location on the unit circle. So a full circle in radians is considered to be 2 pi, and in degrees is 360 degrees. So if we want something that's, let's say, 180 degrees, that means that we're going to have a line that goes here, because this angle right here is 180 degrees. It's also pi. If we give another value like 5 pi over 4, that's going to be 1 pi would be here, and then it's going to be a quarter of a pi. So it's going to be like 5/8 of the circle. So it's going to be this angle here. Now, because it's a circle, this pattern repeats over and over again. And so if we're looking at this input-output map, we can input any angle. So if our angle's more than 360 degrees, we're just lapping around the circle. So if it's 420, well, we go our first 360, and then we have another 60 degrees left. So this is equivalent to a 60-degree triangle. Same thing works with radians. And the idea is you can go in the negatives or in the positives, but you're just looping around the circle over and over again, where we start at the positive x-axis. So that means our input has a domain of infinity. So we can input any values um, between negative infinity and positive infinity, but they have to be angles. However, each value is really equivalent to the specific values between 0 and 360, and 0 and 2 pi. Now again, we can put values outside of this, but they're equivalent because the pattern repeats. And anytime we have a repeated pattern, we describe this repeated pattern, aka how often we repeat the cycle, as the period of the function. So that means for a basic unit cycle, the period is 2 pi, or 360 degrees. Now, we've discussed periods before in both this class and in physics, and the idea is that anything that repeats, how often it repeats is the period. So the amount of time it takes, in this case, the amount of angles that you have to go through until you have the pattern repeat. Now, the output for these is always a ratio, but because all of the values have to fall on this unit circle, then we're restricted or limited to possible values that actually hit for this circle. So since this is a unit circle, the top of this circle is at height 1 because the radius of the circle 1, and the bottom is at height -1. Same thing for the x values. The x values start at -1 and go all the way to +1. So when we're talking about the domain and range of these trig functions, is it depends on these restrictions of our x and y. So for example, sine is all the y values, and we said that sine can only give out values between -1 and 1 because that is the actual y values possible on the unit circle. Cosine similarly is going to have a range between -1 and 1. So sine and cosine have a range between -1 and 1. However, the other trig functions have a slightly different range. So for example, tangent and cotangent, we're dividing x over y. And since x's can be between anything between -1 and 1, and y's can be anything between -1 and 1, we can really form any possible value. So that means the range for specifically cotangent, tangent, and actually secant and cosecant are all going to be from -infinity to infinity. So for cosecant, 1 divided by 0.000001 is going to be a really huge number. Or if I divide by -0.000001, it's going to be a really large negative number. So the range here depends upon how big or small our y values are. And so we can actually go from -infinity to infinity. The same thing is true for secant, and again for tangent and cotangent. Now, other interesting things about the trigonometric functions is that based on their structure, how they operate, um, other patterns or descriptions of how they can be graphed can be viewed. And I'll show you that in a second. Before we do that, let's talk about how to evaluate specific values for a trig function. So if you're given an angle, and let's say that we want sine of 60 degrees, then what we do is we'd find on the unit circle where 60 degrees is, which is about this point right here, and we would be given an x and y value. Now the x value here is going to be 1/2, and the y value is going to be √3/2, and the hypotenuse is 1. And so depending upon which trig function we want, so if we want sine of 60 degrees, then we want the y value here. So that would be √3/2. If we wanted the cosine of 60 degrees, we would want the x value, which the x value here is 1/2. Now, if we go through and we wanted to find the rest of them, tangent of 60 would be y over x. So √3/2 divided by 1/2. That's the same thing as √3/2 times 2/1, or the reciprocal of 1/2, and our 2's cancel. And we just get that that's equal to root 3. For cosecant of 60 degrees, we want the reciprocal of what we had for sine. Now, sine is root 3 over 2, so it'd be 2 over root 3. We'd like to rationalize this, so we'd multiply it by root 3 over root 3, or 1. And when we do that, we'd get the denominator will be 3, and the numerator will be 2 root 3. So we get 2 root 3 over 2, or sorry, over 3. And then for secant of 60 degrees, we'd get the ratio of um, 1 over our x. Now, since our x is 1/2, 1 over 1/2 is 2, or the reciprocal of our cosine. And then finally, for cotangent of 60 degrees, we want the reciprocal of our root 3 that we had before. So we get 1 over root 3, which is equal to root 3 over 3 once we rationalize. So that's how you'd find it if you had a degree. You'd find specifically where on the unit circle. Um, or if it was given in radians, you'd find a similar spot. Now that's for common angles, and the unit circles we filled out previously had specific angles. It was all the 30, 60, 90 triangles. So it had these two here, like if this is a 30 degrees and this one's the 60 degrees, we had these points, and that broke up the circle into twelfths. But again, so if we were doing it with radians, if this is pi, then 30 degrees would be pi over 6. So we'd go pi over 6, pi over 3, pi over 2, and so forth and so on. So 4 pi over 6, aka 2/3 pi, and then 5 pi over 6, and then 6 pi over 6, and then we go all the way around the circle. Now, that was one of the triangles. The other right triangle that we used for common angles was the 45, 45, 90 triangle, where the values were root 2 over 2, which again, you could find using the Pythagorean theorem. So since you know both the x and y values have to be equal, you essentially have, instead of a squared plus b squared equals c squared, where your c is 1, you end up with a squared plus a squared, since those sides are the same. So x squared plus x squared equals 1. And what you end up getting is you get 2 a squared equals 1. You divide both sides by 2, and you get a squared equals 1 over 2. And when you take the square root, you get a equals the square root of 1/2, which is equivalent to 1 over root 2, which when we rationalize, we end up with root 2 over 2, which is why each of these values for 45 is root 2 over 2. So those are the common angles. Now, if you don't have the common angles, all you need is a single x or y value to find the third side. Okay, so let's say they give you a specific trig function. Now they could say the sine of 40 degrees is 0.6428. So what you could do with this information is now you have one side of the triangle. You can form your triangle that's going to have an x, but our y value is going to be specifically 0.6428, and our hypotenuse is going to be 1, and so you can use the Pythagorean theorem to solve for the missing side. And once you have all three sides of a triangle, so if we look at our previous example where we had a 3, 4, 5 right triangle, we could find any of the trig functions for this triangle. Now, notice that this does not have a hypotenuse of 1, so we can't specifically just use the x or the y value. It is where the basic trig functions that we've used in the past are specifically sine, cos, and cosine, and tangent, because these don't rely on the hypotenuse being anything other than 1. And so what we can do here to find an equivalency is we can divide everything by the size of the hypotenuse. So 5 divided by 5 becomes 1. 4 divided by 5, 0.8. And 3 divided by 5 is 0.6. So now this is a similar triangle to the 3, 4, 5 we had before, but this one specifically falls on the unit circle. So it falls at the point of an x value of zero point 0.8, so like right here, and a y value of zero point 0.6. So somewhere on the unit circle up here. And because we now have translated this to a similar triangle on the unit circle, we can now find all 6 trig functions fairly easily. So for sine, we just want the y value here. So sine of theta is going to equal 0.6, or my preference is 3/5. I always prefer fractions. For cosine, it's going to be the x value. So it's going to be, again, 4/5 or 0.8. Now notice this 4/5, if we look back to our original description as sine as y over h, sorry, cosine is x over h, we get 4 over 5, x over h. Essentially, that dividing by h translates this into the specific right triangle that lands on the unit circle. Okay, for tangent, we can similarly divide each of these two sides. So opposite over adjacent, or y over x, and we're going to get 3/4. For cosecant, we're going to get the reciprocal of sine. So we're going to get, instead of 3/5, we're going to get 5/3. Cosecant of theta equals 5/3. Secant of theta is going to equal the reciprocal of cosine, or 5/4. And cotangent of theta is going to be the reciprocal of tangent, or 4/3. So the basic idea is that any triangle you're given, or any x or y value, allows you to find the exact point on the right triangle, or sorry, on the unit circle, assuming that you know whether the values are positive or negative, or which quadrant it's in. So for example, if I just told you that um, the sine of the angle, but I didn't give you a specific angle, was 3 over 5, just like it is in this triangle, we would know that it has the value of 0.6 for the y, but on the unit circle, there's 2 spots that this could be. So we could have a 0.6 here, but we could also have one here. So we don't know whether the x value is positive or negative. And this comes from the fact that when we're doing the Pythagorean theorem, to find that missing side, we have to take the square root. And when we take the square root of this, a squared equals, um, you know, a squared plus b squared equals c squared, but we know the b squared and the c squared is 1. So when we take that square root, it's going to be plus or minus the square root. So it could be the positive or negative version of this. So unless we specifically know the quadrant, we don't know exactly which of these two triangles, the one that goes from the origin up to here, or the one that goes from the origin up to here. We don't know which of those two right triangles, but essentially we know a similar triangle enough to figure out um, the values with possible differences in sign. Okay, so this was the basic how to find your 6 trig values, or the values of the trig functions for a specific spot on the unit circle, or how to evaluate trig functions using the circle. The last thing I wanted to talk about is the idea of even and odd functions. So previously, we just described all of these trig functions as taking in an angle theta and outputting in a ratio. Well, that was when we graphed our unit circle on our Cartesian coordinate system, and the input was the angle, and the output was the ratio of x over the hypotenuse, y over the hypotenuse, or any other combination, x over y over x, hypotenuse over x, and hypotenuse over y. We can graph these trig functions in a slightly different manner where our x, instead of being an actual x coordinate, our x represents this angle. And so we'd start off at angle 0, and then we could break it into different intervals for either radians or degrees. So I could say, oh, this is 30 degrees, 60 degrees, 90 degrees, or pi over 6, pi over 3, and pi over 2. And if we do this for the full circle, we typically use a couple of major points. Um, the most obvious ones are going to be our 0, 90, 180, 270, and 360, or 0, pi over 2, pi, 3 pi over 2, and 2 pi. So if we're doing that, that's going to give us very particular values. So if this is a sine function we're graphing, and we do pi over 2, pi, 3 pi over 2, and 2 pi. And again, we can keep going. This is going to go off forever in both directions. We find something pretty interesting about the pattern this forms when we actually look at the values. So at 0, our y value here is 0. So that means our function's going to start at the origin here. So we're going to start here. And then at pi over 2, we're at the top of our circle. So we're right here. So at the top of our circle, we have a value of 1. So if this is 1 and this is negative 1. So 1, negative 1. So we're going to be at the top here. And then at pi, we're back down to 0 because now we're on the other side here. And then when we're at 3 pi over 2, we're at negative 1. And then we're going to be back at 2 pi to 0. So pi is at 0, then we're at negative 1, and then we're back to 0. And what we end up getting is we get this cool wave pattern. And it's going to repeat over and over and over again. So this wave also goes this way, and it's going to form what we call a nice sine wave. So a sine wave looks like this, assuming that I drew all of those much nicer. Okay, so sine looks like this, and we talk about the period being the first time that this cycle repeats. So we go and we start at 0, and it goes around the circle, and by the time it goes fully around the circle, we're back to where we started, and we're repeating the same exact pattern. Cosine, similarly, since it represents the x values, looks like a very similar pattern, but instead of starting at 0, we're going to start at 1, and then it's going to go to 0, because our x value goes to 0 at the top. Then it's going to go to negative 1, and then it's going to go back to 0, and then back up to positive 1 as we finish the circle. So it forms this sort of U shape. But if we keep repeating the pattern, we end up with the exact same pattern as sine. Okay, now if we looked at these graphs and we thought about what we learned previously about even and odd functions, so even and odd functions have to do with symmetry. So here, every point here in the first quadrant gets repeated exactly in the same spot in not the second quadrant, but in the third quadrant. So it's as if we took these points and reflected them across both the y-axis and x-axis to get an equivalent point. So this is symmetric about the origin. Um, the other way we describe this is as an odd function. So sine is considered an odd function. Now cosine, because of where it starts at +1. Okay. When we look at how it repeats, we don't have to rotate it or flip it twice. We just do a simple reflection across the y-axis, meaning that cosine is an even function. Now, because cosine is even, its reciprocal is also going to be even. So that would mean that secant is also even. Now, sine, and we'll go through the graphs of these other ones at another day, but sine, tangent, and their reciprocals, cosecant and cotangent, are also all odd. So their reflections about both the y and x axes, or symmetric about the origin.